paper session 3 of the workshop. In case you're joining, in case this is your first paper session, we will have 2 20-minute presentations and then the questions and answers pertaining to both the presentations at the end. So please post your questions in the chat. And so without further ado, let's start with the first paper of the session, titled Teaching PDC in the Time of COVID, Hands-on Materials for Remote Learning. I believe Joel Adams will be the presenter, and this work is co-authored by Richard Brown, Susan Matthews, and Elizabeth Shoop.
Thank you, Anshul, and thank you for everyone for attending. So just to provide the usual overview of the talk, we're going to start with the problem and look at goals and strategies for dealing with the problem, have a few live demos, talk about assessing the effectiveness of these strategies, and then some observations and conclusions at the end. So the problem is that this parallel and distributed computing topic is, first of all, challenging to teach. I think probably everyone here would agree with that. And that the COVID-19 pandemic has added to this challenge, that at least most schools, because of lockdowns in your country or state or whatever, that forced instruction to shift from in-person format to a remote format. And this remote teaching brings new challenges. Specifically, how do we provide hands-on PDC learning experiences when the students are remote and maybe asynchronous? So we identified 3 goals. We wanted to provide effective conceptual and hands-on learning about multi-core computing. We wanted to provide effective conceptual and hands-on learning about distributed parallel computing, that is, parallel computing in a distributed memory environment, and to identify what types of PDC educational experiences the learners find especially useful. And to try to accomplish those goals, we came up with 3 strategies. Thinking that learners certainly are going to be remote and maybe asynchronous, we wanted to develop materials for multi-core computing that such learners could use, develop materials for distributed parallel computing that such learners could use, and assess what those learners would find most useful. So the materials for multi-core computing, for each remote learner, we're basically building this off of an approach pioneered by Dave Toth. And in that, he had each learner use a single board computer. They were basically purchased these as part of their course pack. And I think Dave actually got rid of the textbook for the course and replaced that with having them buy this kit. And so we used Raspberry Pis. Dave used Odroid single board computers because they were a little more powerful at the time than the Pi. So we, in addition to the Pi, gave each remote learner an instructional video on how to set it up. Suzanne Matthews, our co-PI, was great about creating those instructional videos. And these in combination, the Pi plus the instructional video for setting it up, supported our hands-on instructional goal. Secondly, we gave them a link to a self-paced interactive module on OpenMP multi-threading using this Raspberry Pi single board computer. The disk image that was provided with the Raspberry Pi included the module's OpenMP software, or the programs using OpenMP for the module. So this supported the conceptual and hands-on instructional goals. And this interactive module was written in Runestone Interactive, which, if you're not familiar with it, it's a platform for creating interactive, hands-on instructional materials, basically interactive textbooks. And so we come to our first live demo. Let's cross our fingers and hope this all works. I'm going to have to stop sharing here and share a different window. And looks like this one maybe. Let's try that. Can everyone see the Raspberry Pi virtual handout? All right, great. It's working. So you see this is a 6-chapter virtual handout. Well, I'll just go drop into a couple of these. Chapter 0 goes over some basics, basically what is a Raspberry Pi and how do you set one up. So here we have the instructional video, the setup video built into this virtual handout, and how you would connect it to a remote system using either PuTTY or a VNC client. For people who've never used a terminal before, and there are some of those out there who are even faculty members, it seems like, the preliminaries on how you use a terminal application on the Raspberry Pi, commands like CD and LS, and some useful terminal tricks like command completion, tab completion, and history using up and down arrows, things like that, and some editor options. Since these are interactive, they will be having to change the source files. And the multi-core systems is basically an introduction to the concepts of what a multiple core, or what a core is, what a thread is, how threads and processes differ. And you'll note here we have a first kind of check your knowledge entry, which this is an interactive question that basically checks, did the person understand the preceding discussion? And we've got these interspersed throughout the handout. So threads, multi-threaded execution, and check your knowledge kind of things for these multi-threaded situations. And then leveraging multiple cores. You can see it's not just multiple choice kinds of check your knowledge questions. There's drag and drop. So, you know, we could drag this, the compute unit of a CPU, we could drag that. I think we can drag that here. I'm having trouble doing it with my mouse, but maybe we drag this one here. No, that's the way it goes the other direction. So the compute unit of a CPU can drag kind of matching sorts of things that way. There's parson problems, kinds of check your knowledge units built into this runestone platform. Lots of different kinds of questions, not just multiple choice kinds of questions. So it's a pretty powerful platform, and I'll jump into the simple parallel program so we can see that. So this is just getting started with a single program, multiple data sort of a example, basically a patternlet written with OpenMP in mind. And the learners would then have this software already on their Raspberry Pi and would then follow along in the directions. So the example here, it gets explained as to what's happening, and then when they run the program, how you run it by typing make, how you can control the number of threads here in the command line, and so on and so forth. Now this particular one has a race condition in it, and I won't go into that since we don't have a lot of time, but again, the student can watch an embedded video to explore what's going on with this race condition, why you're not quite getting the expected results, and how you go about fixing that. So again, here in the very first early example anyway, students are seeing that multi-threading isn't just very simple, even though OpenMP makes it pretty simple. There's a lot of work to be done to avoid race conditions. And I think there's parallel loops here, how you would divide the work up using a domain approach. Again, they can have this program there, they CD to the right folder, run this program, and see the behavior. And the exercise then describes what they're seeing and explains it. All right, so I will stop sharing and jump back to the presentation. And continue on here since time is limited. We also then had distributed computing materials where we used a three-pronged approach. We developed an interactive Google Colab module that covered the basics of MPI using MPI for Pi and Python, and those running on a Google Cloud virtual machine. I'll talk more about that in a moment. We also developed an interactive Jupyter Notebook module that used MPI exemplars on the Chameleon Cloud, which is a, let's say it's quite different from a Google Cloud VM in that Chameleon gives you a full industrial strength supercomputer behind the scenes. And then we also developed an equivalent module to number 2 for running these MPI exemplars on a 64-core virtual machine at St. Olaf. And students had the choice. They basically all started with prong 1 here, doing Google Colab, and then went to either number 2 or number 3 based on their personal preference. All these support both the hands-on and the conceptual goals of our activities. So I'm going to jump back to that Google Colab, which is here, I believe. And I go to a different tab once I get the thing out of the way. And here we have the distributed parallel programming patterns using MPI for Pi, by which we introduce MPI. And so after some preliminary explanations, the person has to install MPI for Pi in the Colab the first time they run this. And then they would have to go past the warning that this is not authored by Google. And it basically, you can think of it as sort of building this program for us. And then after the explanation, you can actually come down and run this program and see this is actually running then on a virtual machine at Google. And this time we got 3 of 4, 2 of 4, 1 of 4, 0 of 4. If we run it again, now it's 1, 3, 2, 0. Every time we run it, we get different executions, and students start to see the non-determinism of this. And the commands for doing MPI are built right in to the Colab notebook. There's diagrams explaining this. We have not yet updated our terminology to the latest and greatest. We're still using the master worker terminology, but we can run this and come down and see its behavior. Greetings from a worker, the master. And again, you can run this as many times so you can get introduced to the master worker approach. Various other things, explanation of parallel loops, how you would go about this in MPI. And here's code to actually divide this up, the iterations by computing the chunk size each process will do, the starting iteration, the stopping iteration, and then you run this and come down and actually see the output, and you can see which iterations a given process is performing. And once again, you can get in and change these things. You can change the number of repetitions, change the number of processes you want to use, changing the repetitions in the actual code here, change the number of processes here on the command line with the -np switch. All right, and there's more and more of this. I won't, again, time is limited, so I'll jump back to the presentation and get over our assessment of all this. So we piloted these materials at a faculty development workshop a year ago. And we had 22 participants, 19 from the US, 1 from Puerto Rico, and 2 from international. The 2.5-day format was day 1 was devoted to shared memory parallelism using OpenMP, day 2 to distributed memory parallelism using MPI, and day 3 to curriculum development. So you've seen some of the materials. We're going to ask in a pre and post survey of each participant to indicate your current level of confidence implementing PDC topics in your courses. The gray indicates the responses, the distribution of responses in our pre-survey, the blue, the distribution of responses in the post-survey. And you can see there we have a statistically significant shift if we look at the delta between the pre and post. A pretty good shift there. The participants in the workshop greatly increased their confidence at implementing PDC topics in their courses. And we did the same thing with a different question. How prepared do you feel to successfully implement PDC topics in your courses? So are you ready to actually do this stuff? And again, the gray is the pre and the blue is the post. An even more significant result. People saw this as a very viable approach, even in down to year 1 kind of courses. The availability of MPI for Pi at schools that are doing Python in their CS1 course. This was a very viable approach as a way to implement PDC into CS1. And for our post survey, we asked another question: how useful was each session for implementing PDC in your courses? Question A, and question B, to your personal development, your professional development. The Likert-Scale was a 6-point Likert-Scale, 5-point Likert-Scale, 1 not at all useful, 5 extremely useful. And you can see all these, both of these responses were seen as very useful. 4.55 or 4.38 for the multi-core computing materials, distributed parallel computing materials. Students, the participants saw this as highly valuable, both for taking PDC into their coursework and for their professional development. So some observations from the more qualitative feedback. Learners found these Raspberry Pi devices highly motivating. The quad-core Raspberry Pi let them see some scalability. Learners can actually touch the CPU, the memory, making this a compelling physical experience, not just numbers on a screen. And that quad-core CPU let learners experience speed up, going from 1 to 2 to 3 to 4 tasks or threads or processes. That video and disk image eliminated technical problems. That was very important in making this less scary for people. And those Raspberry Pi kits that we gave out are relatively inexpensive. They're less than $100 or about $100. So less than the price of some textbooks I could name. And learners could use their laptops as front end, which they found to be convenient. For the distributed memory modules, learners really liked the Google Colab and MPI for Pi as a way to introduce MPI concepts. There was no speed up though. That Google Colab is a single core VM. I wish they gave us the option to go more cores, but we're stuck with what Google gives us for now, at least. So that's a negative. That forces us to go to something like a Jupyter Notebook plus Chameleon or a St. Olaf 64-core VM, something. If we want to truly experience scalability, we need to use one of those options. Participants liked the simplicity of the Jupyter Notebook. Chameleon was a major industrial strength system, 15,000 cores, I think, in their system. But that was difficult to set up. We could not do that on our own. We had to have interaction with Chameleon staff to do that. And providing the 64-core 64-core VM from St. Olaf was a good alternative that let participants see different ways to teach these same topics. We did run into some problems there. Nothing's perfect. We had some eager beaver participants who raced ahead of the instructions and caused the problem. But again, we deal with these things. That's the way a workshop goes. So to conclude, the shared memory materials were effective at achieving our hands-on learning and conceptual goals for Multicore. The distributed memory materials were effective at achieving our goals for conceptual and hands-on learning about distributed parallel computing. And the learners really liked materials that let them work at their own pace and that reinforced the concepts through simple hands-on activities. If you want more information, all these materials are available through the workshop page. It's linked there, or you just go to CS in Parallel and look at the workshops thing and go to the virtual 20 workshop. You can contact any of us for more information. And last but not least, thank you for listening and attending. Please put any questions in the chat. I guess we're going to have the next paper about now and answer questions about both papers at the end. So thank you.
Thank you, Joel. This sounds like one of the many COVID-19 adaptations that have lasting value. And during the Q&A time, if we have a few minutes, I'd love Joel to talk a little bit about future plans, post-COVID plans for this one. Now the next presentation is data-intensive computing models for teaching parallel and distributed computing by Michael Gowanlock and Benoit Gallet.
Perfect. Thank you.
Sorry if I mispronounced the names.
No, you got it perfect. Thank you very much. All right. Yes, so I will be describing my data-intensive computing modules, and I'm from Northern Arizona University. Okay, so the motivation for data-intensive computing modules for teaching parallel and distributed computing, sorry, I'll turn my camera on here 1 second. There we go. Is that the users of parallel and distributed computing, span many disciplines, right? So our users of parallel computing aren't just, computer science students. And so there's a great demand for researchers that can harness the power of parallel and distributed computing and apply it to an application area. So, there's lots of different areas like engineering and social sciences, natural sciences, and other areas. And so the motivation, at least for these modules, is to have modules that are going to be applicable for a lot of different audiences. And so the example that I give my students is that there's this new observatory coming online in Chile. The RUBIN observatories will be carrying out the legacy survey of space and time, and it's going to be hopefully, assuming no COVID setbacks, will be producing we'll have first light this year. And it's going to be generating about 15 terabytes of data per night and about tens of petabytes over the 10-year survey. And so that's a lot of data to deal with. And so in order to do data analysis, it's going to be very limited on a sort of typical workstation or server or laptop, potentially impossible, depending on the subset of the data that a researcher is interested in. And so researchers need to have these competencies in both the domain and the methodological sciences. When I'm talking about researchers here, I'm talking about the domain scientists, say like an astronomer, that may not have a computer science background. And so to really do a good job of data analysis, you'll probably need to harness the capabilities of parallel computing in the case of the RUBIN Observatory's survey that it's going to be carrying out. And then here's another, here's a plot from a paper. It was a survey of 704 NSF PIs, and they asked the PIs what are the unmet needs for analyzing biological big data. And the top three were training on integration of multiple data types, training on data management and metadata, and training on scaling analysis to cloud/high performance computing. So the third one is the one that I'm most concerned with here. And the idea is that it's not just astronomy, in biology also, a bunch of PIs are saying, well, people have great domain science skills, but they could use some more training in parallel computing. Okay, and then the other motivation for this is that at NAU, where I work, we have an informatics and computing PhD program, and so it has emphasis areas in computer science, electrical engineering, and then informatics. And our informatics students have backgrounds typically in bioinformatics, ecoinformatics, health informatics, and astroinformatics. And so all students in this PhD program, it's a multidisciplinary PhD program, are required to take applied math and statistics, computer science and software engineering, and then courses out of their emphasis area that are specific to the their goals in the program. And so the idea is that we're going to get a number of students that are going to have a traditional computer science background, and they will hopefully do okay at learning parallel distributed computing. But I'd also like to open it up to other students, say like somebody that's has a biology or ecology background as an example. So a lot of the students in our PhD program are working with large-scale data sets or simulation, and a subset of these students will benefit from parallel distributed computing. However, often students in domain sciences find learning core computer science concepts challenging, and we all know that even computer science students find core computer science concepts challenging, right? So it's a double challenge there, if you want to think of it that way. So the main idea is to come up with these data-intensive modules that have these applications where students may hopefully can make connections to potentially the research and understand why they're learning certain parallel and distributed computing concepts, and make the course sort of applicable to computer science, electrical engineering, and informatics students. So the way that I've developed these modules is we're using the cluster environment and using MPI to teach distributed memory computing. And it assumes a user submits jobs to a job scheduler. And I just want to point out that a lot of the domain science students actually use the cluster more than the computer science students, because they have a lot of data to process or simulations to run and that kind of thing. So actually the cluster environment in this case is, although many students will be the first time ever using the cluster, and there are sort of hurdles there when they're trying to learn how to use the cluster. Most students will have to use the cluster at some point during their studies anyway, so this might be their first exposure to it, or they already come to the class having used the cluster before. So I created 5 modules, one MPI communication module so that people get the benefit, initial understanding of how MPI communication works, and then 4 data-intensive computing modules. And when I talk about data-intensive computing, I'm using that term to refer to as a data set as being used as input into an algorithm, which is not to be confused with a memory-bound algorithm, so the modules have both compute and memory-bound algorithms, and I'm saying data-intensive just refers to they're using data as an input into the algorithms. Okay, so the modules span, these are the 5 modules. So we have one on MPI communication, just basic point-to-point communication and blocking and non-blocking communication. And then the 4 main modules are computing a distance matrix, sorting, performing range queries, and k-means clustering. And here are just a summary of the student learning outcomes. So in terms of MPI, they learn standard communication patterns, blocking versus non-blocking communication, collective communication, like, reduce and so on. They learn the basics of locality in terms of not locality across a network, but locality in terms of just, a cache inside the processor. So they use tiling to improve cache data reuse, and they look at performance trade-offs between small and large tile sizes. Many of the students, including the computer science students, don't really have very much of a background in computer architecture, or if they did take, computer science students should have taken computer architecture class, but they will, that'll have been years in the past, so they'll have forgotten what locality was, some of them. And then they learn that they can use a tool to make measurements, right? So we use a performance tool to measure cache utilization. We examine the strong scalability of the algorithms that are in the modules. They learn about load balancing, and in particular, how data-dependent workloads impact load balancing. So if you have, some data set where you want to, distribute the data to different MPI ranks, and one rank does, some chunk of the data, but it turns out that based on those data properties, it does way more work than other ranks. They learn about data-dependent workloads that way. And then they compare compute and memory-bound algorithms to understand how the memory bottleneck can limit scalability. And they'll do things like, use one algorithm that's like the brute force, not very efficient algorithm, and find that it has great scalability, and then use an optimized algorithm and find out that it has poor scalability, and understand how the memory bottleneck might affect that. And they reason about performance. So here's just sort of a summary of the student learning outcomes. There's more in the paper itself. So to evaluate the modules, so I evaluated them in my graduate level high performance computing course, and the modules accounted for half of the total grade. We used 2 instruments for assessment. So we used quizzes that were assigned before each module was disseminated and after the module was due, so pre and post quizzes. And we analyzed the quiz scores to determine whether the modules help students understand core concepts. So the idea is, if they improve after completing the module, hopefully that means that the modules were helpful in teaching those core concepts. And we also use free response surveys to understand how the modules help explain parallel and distributed computing concepts. So I could get some qualitative feedback about, how were the modules in terms of, helping students learn core concepts. And then all these quizzes and responses to the surveys were voluntary. Students were motivated to take the quizzes so that they had some additional feedback on their understanding of the material in the class. Okay, so I just want to go over the student demographics. So in spring 2020, so this was last spring, I just finished spring 2021, the course. And so we have one student, a brave undergraduate student in computer science, actually the student did great, master's student in computer science, one informatics computing PhD, that's that PhD program, it's multidisciplinary. So one that was in the computer science track, 2 masters in electrical engineering, 2 PhD students in the electrical engineering track, and then 1 bioinformatics student, 1 ecoinformatics student, and 1 astronomy and planetary science student. So this is a pretty diverse group of students to teach high performance computing to. And then this next semester was far less diverse. So 8 of the students had a computer science background. We had 1 electrical engineer and 1 mechanical engineer in the PhD programs. So this one had 8 students with computer science background. This only had 3 in total that had a computer science background. So in the paper, I did not study the spring 2021 cohort because that just passed, but I wanted to present the results anyway because I had the data and I thought it would be interesting. And also I would just take all of my results with a grain of salt because, or all of my evaluation, because I only have 10 students in 2 cohorts, and that's not a very, very large number. So we have some small number of statistics to deal with. So here's, I'm not going to look at these in great detail, but here's kind of what the raw data would look like. So you have a student number, so 10 students, and their different quizzes that they took, and here's like pre and post quizzes. And so have those for both cohorts, and we'll just get to the summary of those on this slide. So in both cohorts, so this is the total pre and post quiz pairs. We have 42 and 43 roughly equal. So this is showing of the quiz pairs. Oh, I should mention one thing here. If a student only completed the pre or the post, then I got rid of whichever one they did, and it wasn't included because can't really determine if they're improving if they only completed one of the 2 quizzes. So that's why they're pre and post quiz pairs. So the number that were equal were in both cases roughly the same. That means they did the same before and after. Their scores were the same, meaning that there was no improvement after completing the module. This is a number where we saw an improvement in both cohorts. And here's the number where they did worse. So in fact, sometimes students completed the module and then did worse on their quizzes, which is not what you hope to see, but that did happen a little bit. However, of the cases where performance improved, you can see that the mean relative performance increase is actually quite large, right? So of the 19 students, say in the spring 2020 cohort, when they improved on the quiz, there was a great, pretty large improvement. In the cases where they did worse, it wasn't as large, although 27% percent is still pretty large. But that's still encouraging that at least when they improve more than when they did worse. There was one quiz. So this is showing the, for each quiz, corresponding to each assignment, here's the averages, right, before and after they complete the module. There were two cases where the mean scores decreased, which is not what you would expect. I don't know how to interpret that. I just wanted to point that out, though. This one's about equal. This one went down by a few percent there. Overall, though, the quiz scores were higher for the spring 2021 cohort, which we might expect because we have the 8 computer science students right in this cohort compared to the 3 computer science students. But they, on average, their performance increased about 3% in both cases between the pre and the post. So that lends some credibility to the fact that the modules will hopefully be help improving their performance. I should say in the previous slide that I showed before, a lot of them when they're equal are students where they're getting perfect on both, right? So that's good. It probably means that my quizzes need to be adjusted to make them a little bit harder so we can actually see the difference. So yeah, just want to point that out. Okay, so going to the free response surveys, I was curious to know how difficult is the class? You know, you only have student rumors to go by. How difficult is that professor's class and so on? So what I want to do is just ask them, you know, how difficult do you find this compared to your other classes? And I used a 5-point Likert-Scale where 1 is much easier and 5 is much more difficult. And so in that spring 2020 cohort, there were 10% said the class was easier. 50% said more difficult, and 40% said much more difficult. So overall, this cohort found the class, you know, quite a bit more difficult than their other graduate level classes. And then the cohort with the computer science students, half said, you know, it was about equal difficulty, and the other half said it was more difficult. So still on the more difficult end of the spectrum, which leads me to believe that even for the computer science students, the modules are still pretty challenging, right? It's not that they're not challenging enough, and that so that I can accommodate students that don't have a traditional computer science background. Okay, ask them, what aspects of the course did you find the most challenging? Probably this is not going to be too interesting for anybody in this room. Debugging parallel code in C, that's always a challenge. Using the cluster environment, most students said in the first or second assignments they had trouble with the cluster, but once they got going, they said it was fine, but initially they had a difficult time. And thinking in parallel, they found the most challenging, which is what we want them to find the most challenging. So that's good. I asked them what their favorite and least favorite modules were. So in the spring 2020 cohort, a large number of students, like there's the K-means module. I'm not stepping through any of the modules because of time, but they said that the K-means module, they liked it because there's a visualization component where you cluster the data. And then after so many iterations of running the algorithm, you can look at your output and see, does it actually look like it clustered the data correctly? So they know whether they think they've got the correct results or not. In spring 2021, there was no consensus, so students all picked different modules they felt were their favorites. And then the least favorite module, there was no consensus, so students again in spring 2020, they all picked different modules that they thought were their least favorite, and in spring 2021, most students didn't respond to the question. So I hope that means that they liked most of the modules. Okay, then I had another question. So the assignments use the theme of data-intensive computing. Do you think the data-intensive applications were useful for helping you learn high-performance computing concepts? And the students reported they liked the data-intensive applications and that the real-world examples helped them understand core course concepts. So that was another thing they wanted to understand, that the applications themselves kind of help students learn the material. And the other question was, you know, we were online because of COVID. So I asked, was the online format of the modules useful for online learning? And this last semester was taught entirely online because of COVID. And the students, all of them said that the online modules were very useful in understanding the assignment instructions and scope. And they prefer that to like oral instructions in class where, the professor says, here's what you have to do in your assignment and puts up a one-page PDF and so on. So that was quite useful to know that the, more detailed instructions so are quite helpful. Okay, so to conclude, we found that the data-intensive applications were helpful in teaching core parallel and distributed computing concepts to both the computer science, engineering, and the domain science students. The cohort with fewer computer science students found the class more challenging, but they did perform well overall. Nobody failed the class or anything like that. They all seemed to understand the material to a pretty good degree. The modules are useful for online learning, which has been beneficial due to the pandemic, of course. And if anybody is interested in the modules, they are available on my website. Future work includes developing additional modules that capture concepts that are not fully addressed in the current set of modules, so couldn't cover everything in just those modules. Maybe some other modules so that students can have some choice in their assignments. I'd like to develop modules that target undergraduate students because this was for a graduate course. And I'll continue examining additional cohorts of students to be able to make stronger claims about the efficacy of the modules because I only had 20 students in total. And also correlate student educational backgrounds with grades, which I sort of did here, but not to the extent that I would like. And I would just like to acknowledge the National Science Foundation and the administrator of our cluster that answered lots of student questions. Thank you.
Thank you, Michael. Henry, you can take over now.
Okay, I don't see any questions in the chat window, so please add them. But I have a couple for Joel and one for Michael. So let's start with Joel. What's the main added value of using Raspberry Pi instead of just having the students use their laptops? I mean, my laptop has 8 logical cores. Students could use that. They could even conceivably use their phones. But what's the key advantage to Raspberry Pi?
There's a couple things there, I think. One, it's this tiny little device, right? The size of a credit card. And a lot of people, the first time they see those, can't believe it's really a full-fledged computer. And so seeing that illustrates just how far Moore's law has come in making things smaller, smaller, smaller. That you can fit an entire quad-core computer. You don't actually need something the size of your laptop to have a fully functional computer. The other thing is that they can actually see the laptop, like a desktop, as far as the components, is a closed system. It's basically a black box as far as seeing the CPU, as far as seeing the memory, right? You buy a MacBook Pro or a lot of computers these days don't even have an Ethernet port on them anymore, right? They just got these dumb USB, whatever we're up to these days, ports. And so you can't even see the network ports on the blasted things anymore. The Raspberry Pi makes all this explicit. They can touch it. They can, if you are into tactile learning, the Raspberry Pi is a much more tactile device, I think, than a laptop.
Yeah, I agree. I mean, when I was a student, I would have loved a shiny new toy like that.
Yeah.
But how survivable are they once they're given to students?
I was surprised. I mean, these things are pretty tough. You don't need anti-static mats anymore, it seems like, with these things. They're pretty durable. I can maybe pass the buck a little bit to Dick or Libby or Suzanne, who've used these in their courses at the other institutions.
Maybe I'll jump in and say that for the last 3 years, I've been teaching it. It's been the daily machine for a undergraduate. We used to call it computer organization or a systems course, taken by first years, sophomores, juniors. The first year, we actually distributed the kits in plastic bags. We're doing better now. We've got a hard case for them as we give them to the students. But really, there's remarkably little damage. They can, if they have even a bag that they can put in their backpack, but especially if they have a case or something, they put it together, they bring it back, and it doesn't take very much time for them to hook it up either.
Let me add one more thing to answer your original question, Henry, is when you do it on your laptop, or when you have a class full of students do it on your laptop, you get all kinds of laptops. You get Chromebooks, you get, Intel, Windows Surface devices, you get MacBook Pros, and you have to worry about the non-standard. There's not a standard platform when you're doing it on your laptop, whereas the Raspberry Pi takes away all those deviations.
Right. Yeah. Yeah. When you mentioned static, Matt, I would have forgotten that, and I destroyed mine. But I've got a question for Michael. Oh, wait, there's one in the window. This one's to you, Joel. What were the sizes of the remote classes that have used this? How well do you think this would scale to very large remote class sizes like MOOCs?
So if you've got if you're willing to pass off the expense of the Raspberry Pi device to your students, it seems like it would scale pretty well, because you don't, at least that shared memory part, there is no, there's no common bottleneck anymore for your individual students. Each is doing it on their own local device.
But then at $100 per unit, roughly, that could be the limiting factor.
Right. You have some, that's like a textbook is the way we view it.
That's true.
But in terms of going to the distributed environment, something like Chameleon, the main thing there is the number of accounts the Chameleon people are willing to allocate for you as an educational institution, since they're really a research machine. And we haven't run into any issues there, at least with our initial encounters with them. Again, Dick or Libby or Suzanne maybe can comment more.
Well, before you do, I want to leave some time for Michael, because I do have a question there. So Michael, in the classes that you taught, what were the type of educational backgrounds that your students had? Because I did a similar course in the iSchool at Illinois, where I taught master students with diverse backgrounds, everything from liberal arts undergrads to computer science undergrads. And it was a bimodal distribution of grades when we got into the data intensive parallel computing part. They either failed it or they aced it, and there was no in between. What kind of educational backgrounds did you see?
Well, so these are all, so these are all graduate students, except for the one student that in each cohort that was an undergraduate student. And I didn't have a bimodal distribution with the, so I had in the first cohort, I had, ecologist, a biologist, and astronomer, that would probably be the ones where you might imagine that they would struggle the most, but they actually did perfectly fine. In fact, one had never programmed in C before. And I said, it'll be a lot of work on your part, but you can probably get through it. And he was really motivated because he had this enormous data set to process. So in that case, I didn't have like a group of students that really didn't get it, but I also didn't have that many students. I only had 10 in each cohort. So if I had more students, maybe I would see that.
Okay, yeah, I had 20, and I gave them a really large NSF grant data set that they make publicly available, and asked them to do topic analysis. But I didn't specify the language. Some people used Java, some used Python, most used Python, but we had a mix of languages. But it really was, some students just found it extremely difficult.
Mm-hmm. Yeah.
So Michael, how would you anticipate adapting this course for undergraduates?
That's a good question. So I think I would probably, because it's a graduate level course, I have a lot of steps in there where I say, there's a lot of things that you need to do in order to, be able to be successful. And I think that I would have to cut a lot of those out for undergraduates because they have less time than graduate students. I'd have to really rethink about the learning outcomes of each of the modules to make it more suitable for undergraduate students.
That's true. I hadn't considered that. I had graduate students too, so I had more of their time than I would have for undergrads.
Mhm.
David, do we have time for another question?
I wanted to ask one. Was I/O a factor, Michael, when you're dealing with large data sets?
So in the class, we don't do that. We assume everything is nice and distributed to begin with. But that would be an interesting topic to study.
Okay, I think we have time for one more question. Do your modules use existing publicly available data sets, or are data generated as part of the application?
Both. So the data sets are just from the UCI machine learning repository. So they're publicly available. So those ones, anybody can download those.
And how large are they?
Probably at most a couple 100 megabytes, if I had to guess. So the modules are also made so that students can hopefully get to the point where they don't need tremendous resources like cores and MPI ranks to see the sort of the scalability takeaways in the assignments, because computing resources need to be used by other researchers on the cluster as well, and they also get frustrated being in the queue.
Yeah, doesn't look like we have any more questions.
So I think that's we are at time for the end of this session.
Okay, awesome. Thank all the speakers again. Both of the speakers again.
Clap, clap, clap.
Exactly.